Everyone, welcome to the determination of an equilibrium constant KEQ Chemistry 1212 lab lecture. Let's go ahead and dive right in. So, many chemical reactions. There we go. Sorry about that. Many chemical reactions are going to be shown as proceeding from reactants to products completely. Now remember, your reactants are going to be on your left, your products are on your right. Now these equations are going to be written so that a single-headed arrow is going to point to the right toward all the products, and that's going to indicate to you that there are no more reactants left following the reaction, and the reaction is not easily reversed. Now, in the aftermath of a combustion reaction, the products are unlikely to break apart and reform the starting materials, and that's going to be indicated by this single-headed arrow that you see on this particular slide. Now, some reactions proceed to a point of equilibrium. After a certain amount of products have formed, the products begin to react with one another, and this reforms the starting material. So when quantities of your product are reacting in the reverse direction as fast as the reactants are forming products, the system is said to be in equilibrium. Now, the state of equilibrium is denoted with the set of double arrows, one pointing to the right or toward your products and one pointing to the left toward your reactants. Now, the specific reaction that we're going to be studying in the lab for this particular exercise is going to be the reaction of the iron 3 cation complexing with a thiocyanate anion to form an intensely red product, which is going to be the iron 3 thiocyanate complex. Now, this equation is written as the net ionic equation. Okay, net ionic equation, and that's what you're going to be seeing right here on this particular slide. So the molecular and total ionic equations are seen here. This is your molecular and total ionic equations, and you see them here listed for you. Now this is directly out of your lab. You can reference your lab, you can pull a screenshot, whatever works for you. This might be something that's handy to have while you're working on your lab. So if a system is at equilibrium and the rate of formation of products is the same as the rate of reformation of reactants, then the concentration of each species is not changing, okay? I'll say it one more time. If your system is at equilibrium and the rate of formation of products is the same as the rate of reformation of reactants, then the concentration of each species is not changing. Because of that, an expression denoting the rates of forward and reverse reaction is set equal to an equilibrium constant, which we call KEQ. And that's going to equal to the multiplicative product of the equilibrium concentrations of the products raised to their powers of their coefficients. And we're going to divide that by the multiplicative product of the equilibrium concentrations of the reactants raised to the powers of their coefficients. And this, what you see on this slide, is just a generic formula explaining basically what I just said to you. So this is going to be kind of a formula that we're going to follow. Now, this equation that you see represents the generic equilibrium expression for the reaction. You're going to note that the square bracket is the symbolism denoting your concentration. So any square bracket that you see is going to denote your concentration. And you can see that on the last slide, which is over here. And we're going to move right over here to where we have brackets. So if KEQ is a large number, then the chemical equilibrium favors the formation of products, and there's going to be a large numerator. Vice versa. If the KEQ is a small number, chemical equilibrium is going to favor the formation of the reactants, and there's going to be a large denominator. So this is kind of an insight into that. So for this experiment, you're going to be able to calculate the KEQ for the reaction where your iron 3 reacts with your SCN to produce the FeSCN or iron 3 thiocyanate. In order to calculate KEQ, you're going to need to determine the concentration of each ion in your solution mixture at equilibrium. You're going to use this equation right here to calculate that, okay? So you're going to be creating a calibration curve of absorption versus concentration of the iron 3 thiocyanate, the calibration curve can then be used to find the concentration of any equilibrium solution based on the absorption of that solution. If you remember Le Chat's, if you've talked about Le Chat's in lecture, we will touch on Le Chat's going forward, but if at equilibrium a change is applied to a system, the species is going to react to offset the change, so it will maintain the equilibrium. We will use the principle to aid in the preparation of a calibration curve. Now, your calibration curve is going to be made by plotting the absorption of the red iron 3 thiocyanate complex versus its concentration. Now, if the concentration of the reactant, which is your iron 3 nitrate, is increased or bigger or larger, then the reaction is going to be forced almost completely to product. If you consider the reaction in terms of the net ionic equation in this experiment that we're actually talking about, the iron 3 concentration is going to be approximately 100 times that of your thiocyanate. Therefore, essentially all the thiocyanate is going to react to produce the red color product. Within the limits of our detection apparatus, which is your spectrophotometer, your final concentration is going to be equal to the initial concentration of the limiting reagent. The intensity of the red color is going to be measured spectrophotometrically, that is a hard word to say, and will relate directly to the concentration of the iron 3 thiocyanate species. Now, after a calibration curve is produced, your conditions or the conditions are going to be altered so that the concentration of each of the two reactant species is going to be the same order of magnitude. Because your concentrations are going to be so similar, no longer be forced essentially all the way to the right or toward the products, and you're going to be able to determine an equilibrium constant from your data. Now, your concentration of your product is going to be determined spectrophotometrically, which this is a spectrophotometer, and the way that works is going to be by relating absorption to the calibration curve. You guys know that our spectrophotometer doesn't exactly look like this, but this is a spectrophotometer, and hopefully you guys can remember what we already played with in previous experiments. So based on the stoichiometry, for every mole of the red complex produced, 1 mole of iron 3 and 1 mole of thiocyanate is going to have been reacted. The remaining equilibrium concentrations that are formed from the initial concentrations before your reaction took place. And this just kind of gives by step how we're getting there, okay? So you can set up an ice table, you can find the equilibrium concentrations for each of the 3 species and solve for KEQ. This is a valuable tool. You're going to be setting up ice tables in this particular experiment. If you're confused about that, make sure you sign up for tutoring, visit the tutorial center, whatever makes you comfortable. So each of the initial solutions are going to be made up so as to contain the 0.500 molar hydrogen, therefore, when you're mixing the solution, no matter your proportions, the concentrations are going to be constant. And the reason the reaction has to run in a concentration of at least the 0.500 molar acid is to prevent significant iron hydrolysis that reduces the concentration of your iron 3. All right, now the reaction must be run at acid concentration below 0.7 molar because otherwise your reaction affects the equilibrium by reducing the available thiocyanate. So that's going to be the end of the lecture. If you have questions, make sure you're reaching out to me, to someone in the tutorial center, whatever your case may be, and I look forward to it. So good luck in the upcoming lab, KEQ.